Hi, my name is Marcelo. I'm a postdoctoral researcher at the University of Helsinki. In this short presentation, I will present key ideas in the UAI paper entitled Flexible Prior Elicitation via Prior Predictive Distributions. This is a joint work with Georgi, Agiashvili, Bürkner, and Arto, Klami. In the context of machine learning and statistics, prior elicitation means transforming someone's beliefs in opinion about a quantity or an event of interest into valid probability distributions. In the Bayesian approach, we would like to acquire information on parameters of a model and transform that into a valid probability distribution, but not the prior. This is not an easy task since the parameters are not observable quantities. As Bayesians, we believe that the prior distribution should be well designed, such that the inferential task and decision-making purposes are improved. In order to ease the problem of finding priors directly on parameters, we will acquire information on what the observable data would look like, and transform such information into suitable prior distributions on parameters. We will also provide measures of model fitness, meaning if the probabilistic model for the data and the prior distribution are able to reproduce someone's beliefs over the data. Before we dive into the key notions of our method, let's recall some basic elements of the Bayes theorem. In Bayesian modeling, we start assuming a probability distribution for the data conditioned on theta to represent the randomness in the data. In turn, a probability model is chosen for theta, the prior distribution. Conditioned on the sample from the probabilistic model of the data, Bayes' theorem combines data and prior distribution into the so-called posterior distribution that summarizes all the information with respect to theta. The prior distribution has its own parameters, henceforth called hyperparameters. It's a distribution that should be designed independently from what the data should look like. The key notion of our method lies in the prior predictive distribution. It's a marginal distribution. It's a distribution in which the effects of the parameters have been marginalized out. We believe this is the distribution that would represent opinions purely on the data. We can now state an inverse problem. Given opinions purely on the data, here represented by the prior predictive distribution and the probabilistic model for the data given theta, find the prior distribution such that one holds true. Although it is difficult to provide any mathematical formula for the prior predictive distribution, it turns out we can provide information where the data would lie in the sample space. Meaning, we can provide prior predictive probabilities in an easy and flexible manner. Once that is done, transform that information into suitable prior distributions. Let's take a closer look. Let omega be the set of all possible outcomes of an experiment. Consider a partition of omega, a set composed by subsets of omega that are pairwise disjoint. Note that there are many ways of finding a partition. In practice, find that one which is the most comfortable for the user. Associate probabilities to each set in the partition, here the PI, the data, and think that each of the probabilities could be modeled via the prior predictive probability. The second key notion is to think of the probability data as a realization of a Dirichlet process, with base measure given by the prior predictive probability with concentration parameter alpha. Note now that the DP inherits the hyperparameters, lambda. Once the data is given, meaning the probabilities are associated with each set of the partition, the likelihood of the hyperparameters is formed. See equation 2. The Dirichlet process captures the uncertainty in the numerical specification of the probabilities Pi, and we can show that the role of alpha is to behave as an indicator to whether the prior predictive probability is able to reproduce users' opinions. We have showed that, approximately, alpha is basically the inverse of the KL divergence between the theoretical prior predictive probability and the probabilities specified by the user. The larger the KL, smaller the alpha, and vice versa. In a plot, the black line represents the prior predictive distribution, and the blue bars the probabilities specified by the user. When there is a good fit between the black lines and the vertical bars, the KL divergence is smaller, and consequently larger the alpha. Let's take a look in a real case example. Consider a deterministic model for the human growth given by the function of ht with the parameters theta. T is measured in years and to be considered as a covariate or feature, and h of t is the stature at the year t. The parameters h1 is the average adult height, s0 and s1 are constants. T star is the time when the adolescent growth spurt happens, and ht is the height when the adolescent growth spurt happens. We embedded the human growth model into the stochastic Weibull model to account for the randomness in the data. There is an extra parameter b which controls the uncertainty around the values of ht. Since all parameters are positive, it will give you log normal distributions to all of them with its respective hyperparameters. For each 4 different time points, see the paper, we asked the user to specify probabilities of the data for a given partition. Once the probabilities were given, the likelihood was formed and maximized with respect to the hyperparameters. The table shows one experiment conducted with a real person. We note that the expected value of the parameters obtained via predictive elicitation is closer to a reference value when compared to the expected value obtained via direct elicitation on the parameters. Variance of the parameters are smaller in the predictive elicitation for all parameters. Our measure of quality, the alpha value, is higher, meaning that the prior obtained via the predictive elicitation better reproduce the user's opinion. In order to help the user and enhance its experience with the method, we have created a graphical interface with our language using the package Shiny. This interface was based on an existing platform called Shelf, developed in the University of Sheffield. See details in the paper. Another important contribution of our paper is in the method developed to optimize the likelihood function. We have provided algorithms based on natural gradients that suits well both cases when the prior predictive probability is given in closed form or not. For the common cases when the prior predictive probability is not given in closed form, we provide a new multiple stochastic algorithm based on pivotal quantities to estimate the elements of the feature information matrix. Lastly, we present some remarks. Our method can deal with hierarchical models with any number of layers. It naturally accommodates multivariate priors covariates with powerful inference algorithms. In future, we look for find good partitions such that they provide the maximum amount of information on experiments for the hyperparameters. We also look for alternative methods to decrease the burden of a cognitive effort to specify probabilities. That's all, folks. Thank you.